7E, counting and probability. In this section, we will be using different counting methods to find out, to help us count the number of outcomes, whether it's for the event or the total number of outcomes. First, we are doing arrangement with repetition. Let's think about telephone numbers, a 7-digit telephone number. Now, if we think about a 7-digit telephone number, we can imagine that there are 7 blanks, right? There are 7 blanks where we can put in different numerals, different digits. I can have anything from 0 to 9. Okay, suppose anything from 0 to 9 is possible. So I can have perhaps a 4, right? But it can be also 3 is allowed, 2 is allowed, 1 is allowed. And I can have 0, I can have 9. But for each of them, let's imagine the very first digit. How many possible choices are there? Because I can choose digits anywhere from 0 to 9. And we happen to have 10 possible choices. 1, 2, 3, 4, 5, 6, 7, 8, 9 plus 0. So that's 10. For the second digit over here, same idea. We have 10 different choices that we can possibly make. And then it's another 10, and then it's another 10. And remember, what we have to do is we have to multiply them, right? Because there's sort of 10 possible 10 choices for the first digit, and then 10 for the second, 10 for the third. They are like independent events. So we multiply them together like this, and we ended up with 10 to the power of 7. Right? We multiplied 10 7 times. And that's why often we will use the exponential notation to represent it. So in this case, it's 10 to the power 7, or 10 million different numbers. The second way that we can do the counting is through something called permutation. Let's suppose we have a team of 4 swimmers. We will call them, we can call them Ashley, Brittany, and perhaps we have Cindy, and Diane. Suppose we have 4 people, A, B, C, D. Now, we want to order them. Okay, we want someone to go first, someone to go second, someone to go third, someone to go fourth. We want to order them to form a team. You notice how we have 4 different slots, right? Someone to go first, someone to go second, someone to go third. In the first slot, we can pick any of these 4 people. So we have 4 possible choices. But in the second slot, suppose Cindy gone first already. We only have 3 people to choose from now to take the second spot. And after we choose a person to go second, we only have 2 people left for the third spot, and then 1 person left at the end. This is called permutation. And this is what we will do if the order does matter, right? We want someone to go first, someone to go second, someone to go third, someone to go fourth. We multiply these numbers together, and in total, we get 24. So in this particular case, we have 24 different outcomes, or 24 different choices. Often, it's a lot of work to put all the different numbers into your calculator. So what we'll do is we'll use the factorial symbol. We'll do 4, and the exclamation mark is called the factorial symbol. So 4 factorial means that we're taking 4 and we're multiplying 3 to 1 all the way down to 1. This will give me 24. Suppose we have 6 different classes and we want to arrange them. In 6 different time periods. How many different schedules are there? Once again, imagine that we have 6 different time slots. Period 1, period 2, period 3, period 4, 5, 6. And at the very beginning of the day, we can go to any one of these 6 classes. So we have 6 different choices for the first class. And perhaps I have history first, then I only have 5 different choices to go for my second period class. I might have science second. And then we only have 4 classes left. So 4 times 3 times 2 times 1. Remember, we are multiplying all these numbers together. We can also simplify this as 6 factorial. We can simply do 6 factorial, and that's 720. You can put 6 factorial into your calculator, and you should get 720. Now, perhaps we have 10 different swimmers on our team, right? We don't just have our 4. So we don't just have our Ashley, Brittany, Cindy, and we have D, E, F, G, H, I, and perhaps we have Jackie. So we have 10 different swimmers. In this case, we still have 4 different slots, 4 different people to choose to put on my team. For the person to go first, I can choose any of these 10 people. I have 10 different choices. But suppose I pick someone to go first. Suppose I pick Elaine to go first. I only have 9 people left to choose from the second spot. And then 8, and then 7. This is called permutation. This is represented as 10p4. We have 10 people to select from, 10 different choices, and we want to select 4 in order. Some calculators will allow you to put in 10, and then you'll be able to find the NPR button somewhere, and you'll do 10 NPR4 in your calculator. For our questions, most of our questions will be simple enough that we can just use the method that I just showed you here. We can find out how many different choices are there in each of the slots. And we can just multiply 10 by 9 by 8 by 7 and find our answer. In some cases, the multiplication can get very big. So we can also do a shortcut. In this case, because I have 10p4, we have 10 factorial divided by 10 minus 4 factorial. And turns out 10 factorial divided by 10 minus 4 factorial, that's just 6 factorial. What this tells us is that in the numerator, we have 10 times 9 times 8 times 7 all the way down to 1. And in the denominator, I have 6 times 5 times 4 times 3 all the way down to 1. And we can sort of factor out the 6, 5, 4, 3, 2, 1. And that's how we ended up with the number that we want. So you notice we factor out the 6 factorial part, 6, 5, 4, 3, 2, 1. If we multiply everything together, we have 5,040 ways. Suppose we have 12 candidates and we have 3 different positions. The 3 positions are different. We're not numbering them first, second, or third, but the 3 positions are different. We have a mayor, we have a deputy mayor, and we have a chief financial officer. In these cases, the 3 positions are different. It's like having a gold medal, silver medal, bronze medal, first, second, third. For us to find the total number of outcomes, the first position, the mayor, we have 12 people to choose from. The second position, we have 11, and then we have 10, and we multiply these numbers together. In the end, we should have 1320. So there's nothing wrong with writing the 12 times 11 times 10 directly if you know how to get there. But you can also remember the formula 12p3. In this case, order matters. We have 12 people to choose from, 3 different positions. Something that's slightly different is called the combination. In combination, the order do not matter. Suppose we have we have 3 different flavors: apple, banana, cherries of ice cream to choose from. Now I know these are not common flavors of ice cream, but I just wanted to pick something that's A, B, and C. And suppose you want to pick 2 different flavors. Now we have, if I try to write everything together, if I try to write everything out, we can have apple and banana, apple and cherry, banana and apple, banana and cherry, cherry and apple, and cherry and banana. Now, if I give you a bowl and it has apple on one side, banana on the other side, you have 2 scoops of ice cream, you might not like it. You might think that apple and banana ice cream doesn't go together. And you will say to me, I want a different flavor. Now, if I bring out banana and apple, I'll bring out banana and apple in a different bowl, and I give it to you, you would tell me that that's exactly the same as the apple banana ice cream that you just got. We just turn the bowls around, right? A little bit. In this case, it's still the same 2 ice cream combined together, and they still don't go well together, and we don't like them. In this particular case, that means apple and banana and apple are the same. And that's the big difference between combination and permutation. In this case, the arrangement do not matter. So apple, banana, and apple are the same thing. So in essence, we really only have, right? We only really have 3 different combinations. We only have 3 different combinations. We have apple, banana, apple, cherry, and banana and cherry. Now you'll notice in this case, we still do what we normally do for permutation, right? We think about there are 3 flavors to pick first, and after I pick the first flavor, we have 2 flavors left. But you'll notice once I select a set of flavor, apple and banana together, I can rearrange them, right? I can rearrange the A and the B. Here I have 2 different letters, A and B, apple and banana. I can rearrange them. I can give you apple first, or I can give you banana first. So that means we have 2 times 1. I can rearrange the 2 different flavors in the 2 spots like so. In this case, we get 2 different arrangements. And that means we double count all the permutations, all the different outcomes that we found earlier. We double count them. We count each of them 2 times. So I take 3 times 2 divided by 2 times 1. And this is why we have the extra we have the extra term in the denominator to divide out all the double countings, triple counting, or duplicates that we have of the same set. Now, suppose we have 12 ice cream flavors in total, and we want to select 3 of them. How many different combinations are there? Well, we do the same thing. We have 3 different flavors. The first flavor, we have 12 of them. The second flavor, we have 11. And then we have 10 flavors to choose for the third flavors. But we count the set that we choose. Let's say we choose apple, banana, and cherry. Let's say these are the 3 that we pick. We have different ways that we can get the combination of apple, banana, and cherry, right? I can have apple first, I can have banana first, I can have cherry first. So we can, with these 3 flavors, I can have any of these 3 first, and then two left for the second spot, and I have 1 more in the last spot. The bottom is equal to 6. That tells me each combination, ABC, there are 6 different ways of organizing them. And we want to divide that. So in the end, what we want to do is to do 12 times 11 times 10 divided by 3 times 2 times 1. You can do it like this, or you can use our formula 12 factorial divided by 9 factorial times 3 factorial in the denominator. But you'll notice, after we factor out the 9 factorial, we have 12 times 11 times 10 divided by 3 times 2 times 1. And in this case, we get a total of 220 different flavor combinations. Now, if we want to to extend this a little bit, the counting that we are doing, we can use these counting to find probabilities. Suppose we want to find a royal flush of hearts. You notice there's only one outcome that gives me the royal flush of hearts. There's only one set of 5 cards, and they are the ace of heart, the kings of heart, the queens of heart, the jack of heart, and the 10 of heart. I cannot substitute any of these cards with anything else. We're not playing with jokers here, so no jokers. Okay, no wild cards, but just the standard deck of 52. So in this case, what we needed to do is to find the total number of outcomes to divide. Right? We know that we have one outcome that gives me the royal flush, but how many total outcomes are there? Well, when I have a hand of 5 cards, when I get 5 cards in my hand, it doesn't matter which card comes in first. What's important is I have 5 cards. Because order doesn't matter, we are doing the combination. It's like picking 5 different ice cream flavors. We don't care which one comes first. So in this case, we're doing 52 factorial divided by 47 factorial and 5 factorials in the numerator and in the denominator. So in this case, we'll end up with 52 times 51 times 50 times 49 times 48 divided by 5 times 4 times 3 times 2 times 1, all in the denominator. Now, if you do this by hand, remember to put in a bracket or do the denominator separately so that you are not making a mistake. If I divide that, you'll notice I have roughly 2.6 million different heads, right? Getting a 5-card head, there are many, many possible combinations. Now, the probability to get a royal flush is very rare. It's 1 over 2.6 million. It's actually very rare. It's almost like winning a lottery. Not quite, but almost.